Okay, I think we will start, and I hope others will join meanwhile. And there are actually 7 people already. Okay, so today's lecture is going to be dedicated to kinematics models of wheeled robots and probabilistic motion models. As usually, you can open slides on your devices if you wish. So today we are going to talk about kinematic models of different types of wheeled robots. We will discuss differential drive, tricycle. We will also talk about Ackermann steering principle, and we will shortly discuss Omni and mecanum wheels, which are really interesting types of robot wheels. And the second part of the lecture will be dedicated to probabilistic motion models. And we will discuss 2 major types of such motion models. And I remind you from the last lecture that we were discussing recursive Bayesian pose estimation. This is a framework used for pose estimation in modern robotics. And we have 3 major parts here. We have a recursive term, which is previous system state in blue. We first apply motion model to this recursive term, and then we apply some observation or measurement model to estimate our current pose. I will also remind you that this is just a framework, so we cannot use this equation directly to estimate robot pose. There are different algorithms which are following this framework to help us to estimate robot pose in space. And last time we discussed so-called Kalman filter, which uses normal distributions and their multiplication to estimate probability of robot pose. And we also discussed particle filter, which uses hypothesis or particles to represent probability density function by discrete particles, and by propagating them with motion and observation models, we also can estimate robot pose. So these are 2 algorithms we discussed last time. If you have some questions regarding these algorithms, you can ask right away, and we'll remind ourselves what these algorithms are. And today we are discussing motion models, because while discussing particle filter and Kalman filter, we saw that there are some motion models involved. Here it is in particle filter, and in Kalman filter, the first equation represents motion of the system, motion of our robot. So we just said that there are some probabilistic motion models, but never discussed them. So today we're going to discuss exactly this term of this equation, motion model. As we see, this motion model connects previous pose, previous system state with the current system state, and it uses so-called control signals, U. So these control signals are signals we are commanding our robot, or commands we are giving our robot to move in space. And it has probabilistic form because our motors are not precise and our motions are not precise. And we will discuss it further, what are sources of uncertainty in our systems. But before discussing probabilistic motion models, we have to discuss what types of kinematics there are in wheeled robotics and what are the differences between them. So we will start from wheeled robots kinematics. And this slide presents you different types of kinematics used in robots. So there are 2-wheeled, 3, 4-wheeled robots, robots with 1 steering wheel, robots with a car-like kinematic when we have 1 axis which is steering our robot. There are also more sophisticated types of kinematics, and these orange wheels are called omnidirectional wheels or mecanum-wheels. They allow robot to move in different direction and to immediately change the direction of our velocity. We'll discuss it further away. So we will start with term holonomic or non-holonomic systems, because it is important for us to distinguish those 2 types of systems. So a robot is called holonomic if the number of controlled degrees of freedom is equal to the total number of degrees of freedom. What it means in practice is that we can control any degree of freedom of our robot. So basically, in case of wheeled robotics, we can move to any direction. And non-holonomic system is a mechanical system on which, in addition to geometric or to holonomic constraints, there are also kinematic constraints. And mathematically, non-holonomic constraints are expressed by non-integrable equations. So this sounds a bit complex, and we will not go into the details, but on the slide, there are two types of system. On the left side, there is holonomic system, and you can see that it can move any direction, like sideways. It can change its orientation in place. And on the right side, you can see a typical car, which is non-holonomic system, because car cannot move sideways. And that is why, for example, to park a car, we need some complex maneuvers, because we cannot control all degrees of freedom. We cannot move sideways, and such system is called non-holonomic. And majority of robots used in practice are non-holonomic. However, if you ever saw like vacuum cleaner robot, it is holonomic, because it cannot move sideways, but it can change its orientation in place and continue moving to any direction. So a bit more into holonomic and non-holonomic. Holonomic constraints are constraints which only limit the allowed state space, and they are also called geometric constraints. For example, if you have a truck and a trailer, not all angles between them are possible, right? Because we cannot turn 180 degrees with a truck if we have a trailer, and you can see this on the slide. And this is called holonomic constraints because it doesn't limit our degrees of freedom. It only limits some state space. So not all angles are possible. And non-holonomic constraints limit the control space to relative to the current space. It means that having our current state of the system, for example, pose of the robot, we are already limited with further actions we can take. For example, if we have a car parallel to the side of the road, we cannot move sideways, right? We will have to complete complex maneuver to like change a lane, for example. We cannot just move sideways and change a lane with a car. But there are, as you can see on the slide, some interesting cars which actually can turn their wheels exactly to solve this problem, to make a car a holonomic system. So I hope it is clear with holonomic and non-holonomic. If you have any questions, you can ask right away or type in chat your questions. So, and also two important terms we need to discuss is inverse and direct or forward kinematics problems. So there are two problems in kinematics. I hope you are familiar with these terms. The direct kinematic problem stands for the problem when we have control parameters, for example, wheel speeds or steering wheel angle, and we have a time delta in time which we are moving, and we want to find the position into which the robot has moved. So once again, as an input, we have control signals, for instance, linear velocity, angular speed, and so on. And what we want to solve when we are solving direct kinematics problem, we want to find the robot pose in the future in some increment of time. And there is other problem called inverse kinematics problem. In this problem, we have a desired robot pose. For instance, we know where we want to move, and we have to compute control signals we need to apply to robot to move to this pose. So in the forward or direct kinematic problem, we are finding robot pose given the control signals. And vice versa, with inverse kinematics problem, we are finding control signals which we need to apply to our robot to reach the desired pose. These are two inverse problems. I hope it is also clear. And so we are starting to discuss particular kinematic types of robots. And we start with differential drive. as we already said, it is quite common in vacuum cleaners, and you can see this is a robot in our lab, which is built upon the vacuum cleaner robot, and this is quite famous research robot called Turtlebot, and used a lot in laboratories all over the world to study some simple motions and so on. Yeah, and on the right side of the slide, you can see just a vacuum cleaner, which also has differential drive. So differential drive is the simplest drive when we have two wheels controllable separately, so each wheel can have its own speed. And here on the slide, you can see this. So VL and VR are the left and right wheel speed correspondingly. So these are our controlled signals. We can control these velocities of right and left wheel. Also, we have a robot pose, which is represented by a single point, which is center of axle. This point has coordinates, and we also have orientation of our robot theta. And another important term here is instantaneous center of curvature. This is center around which robot rotates in some short period of time. That's why it's called instantaneous, because it can change over the time. But for the short period of time, it stays constant. At least it's our assumption. So given all that, we will derive following equations. So right wheel speed is equal to angular velocity multiplied by radius of the rotation, which is radius from instantaneous center of curvature to the center of robot, plus half of L, which is the width of our wheelbase. So it's called wheelbase, and it is different. It is distance between centers of two wheels of the robot. So L is the distance between two wheels, and half of L is distance between our center of our axle and center of our right wheel. So we can derive two speeds of our robot, but actually we control those speeds from by ourselves. So knowing these two speeds, we can derive angular velocity, we can derive speed of the robot as a average of left and right wheel speed. And also we can derive radius. It is also instantaneous radius of rotation, because it will change over time when we apply new speeds to our wheels. But for the time moment, we can derive all three, just having just given our right and left wheel. Is it clear? Do you have any questions maybe here? Okay. So once again, we are controlling speed of right and left wheel, and given that, we can derive angular speed, angular velocity, radius of rotation, and basically having angular velocity and radius of rotation, we can derive future pose of our robot. And there are three types of motion available when we are operating with differential drive. If we have our speeds equal, so speed of or velocity of left and right wheel are equal, we will get just a linear motion. The radius of rotation is infinity, and angular velocity is 0, according to these equations. So if two speeds are equal, we will have 0 in denominator, and radius will be infinity, and here we will have 0 in numerator, and angular velocity will be equal to 0. So, and robot will move just straight if it is quite obvious. If we have equal velocities of our wheels, robot just moves straight. If we have inverse velocities of our wheels, we will rotate around the center of our robot. It doesn't matter like which wheel rotates where, we will just rotate either clockwise or counterclockwise, and the radius of rotation will be 0. And this is important feature of differential drive, because we can just rotate in place, which is really convenient when we use differential drive. For example, if you ever saw vacuum cleaner robot, they use this feature a lot. They often rotate in place because they're operating in really confined spaces, such as living rooms, where there are many obstacles, such as chairs, tables, and so on. So these robots have to rotate in place to change direction of their motion because they operate in really confined spaces. And the third case, if speed of one of the wheels will be equal to 0 and the speed of other wheel will be not equal to 0, we will rotate around the left or right wheel, depending on which speed is 0. And radius of rotation in this case will be equal to half of wheelbase, L divided by 2. And we will perform like circular motion also in almost in place with a radius of rotation L divided by 2. So these are three motion patterns available when we are operating with differential drive. And we can compute instantaneous center of curvature by using simple triangular geometry formulas. We will not go into details here. I hope you can derive them on your own, but just for the moment, take it for granted that this is equation for instantaneous center of curvature. And using this, we can derive like future pose of the robot using these equations written in matrix form. Here, delta t is a time increment, which we use to like predict robot pose in future. But just by using simple geometry, we obtain these equations. So x dot is a future pose where x is a current x coordinate and so on. So omega delta t is just increment of orientation of robot. So using angular speed and delta t, we can compute how much robot will rotate. And then just using simple geometry, we can recover the future pose because we know that the robot is moving around instantaneous center of curvature. So this is just simple geometrical equation. Yeah, and we can also always answer the question where a robot is within some time interval, because we can integrate linear and angular speeds. And just always by integrating, having a time increment, we can always answer where we ended up our motion. And here, velocity, as you remember, we can compute having velocities which we are actually controlling, velocities of right and left wheel divided by 2 to get velocity of center. And also omega we can compute knowing speeds of our wheels. And also here we just need to know the wheelbase of the robot divided by 2, and we get the angular velocity of our robot. So basically these equations is everything we need to know where our robot in space within some time period, if we knew the initial pose we started. There is another model called Tricycle. It is almost the same, but here we have one additional third wheel, which is steering wheel. So now we are not controlling just separate we are not only controlling just separate velocities of two wheels we had, we also control angle of our front wheel, which is called steering wheel. And the equations are almost the same. So for angular velocity and for radius of rotation, they're exactly the same, as you can see. And the speed of this rear steering rear axle is the same. You can see that this speed is still the average of speed of left and right wheels. And the only difference in the whole equation is this. So now we can compute radius differently, radius of our rotation, because using angular formulas, we now have new parameter d, which is length of our robot, basically length between rear axle and front steering wheel, the centers, of course. And now radius of rotation is computed differently, and all the rest of equations are the same for 3 cycle. But having such scheme, we're actually losing some properties. Now our robot cannot rotate in place because we have third wheel, which is steering wheel. We cannot rotate in place. And actually now we have to think about such a complex concept as Ackermann steering geometry, because now our wheels have to rotate with different speeds, and just imagine these two wheels will be connected, which means they're rotating with the same speed. In this case, by rotating, we will have one wheel to rotate faster than another, and if these two wheels are hardly connected, then it means that one wheel will be slipping all the time, because wheel which is moving on a bigger arc will have to rotate faster. If there is hard connection, the wheel which is moving on a smaller radius will have to slip in order to keep on with a wheel which is moving on a bigger radius. And this is why Ackermann steering geometry is concept which is widely used in our cars, because actually this is quite similar to the car geometry, only except one wheel in steering axle instead of two. So in cars, you have such a concept as differential drive, which allows your wheels to move with a different velocities, even though um, they're rotated by a single motor. They still can move with a different angular velocity. This is due to these factors that on the turns that they will have to rotate with different speeds, and that is why they're detached one from another, and this is called differential uh, in cars at least. And Ackermann steering principle, which we started to discuss, this is a steering geometry principle designed to allow steering wheels to go around circles of different radius and to avoid slippage. So basically on here on the image, you can see that right and left wheels of the car are moving on different radius. And as we said, for rear wheels, they will need a differential to move with different speeds. And for the front, for steering axle, we will need just to use different angles to rotate wheels on different angles in order to accomplish such maneuver, in order to allow wheels to move on different radius. So as you can see, Ackermann steering principle just allow us to turn wheels on different angles, and that is why they can move on different circles, and we will not have slippage. And talking about equations, there are quite simple equations also derived from triangular geometry. And you can see that closer wheel, this one, will have smaller radius of rotation, and this wheel will have bigger radius of rotation. And actually, when we're talking about motion models, when we are modeling robots kinematically, we usually substitute these two complex wheels with different radius of rotation with a single wheel, which rotation radius is like average of those two. And this quite simplifies us mathematics in our kinematics models. And this is still quite close to the reality, because if we had the third wheel in between those two, it would move on the circle which is between those two circles, which radius is average of these two radiuses. So to simplify our mathematics, we usually use this trick. We just imagine that we have not a car kinematics but three cycle kinematics, and we imagine that we have one wheel in the middle. So this is how we usually work with kinematics of a car-like robot. So there is also quite complex types of wheels which are called omnidirectional and mecanum-wheels. We will discuss them separately, but we will not go into the details. You just have to know that there are such type of wheels and such type of robots. So omnidirectional wheel is a wheel which allow robot to move 90 degrees perpendicular to the wheel orientation. But for that, you will need to have some complex arrangement of wheels. For example, on the right image, there is triangular robot, and it wheels on 60 degrees one from another. So it has three separately controlled wheels, 60 degrees one from another, and you can see that it allows robot to move basically any direction. So it is a holonomic robot. It can instantaneously change direction of its motion. Um, and this is done by omnidirectional wheel. But for example, you can imagine the situation where the robot moves, for example, to this direction, and one wheel is just not rotating actively. It just uses rollers to allow rotation to this direction. And on the bottom of the slide, there is quite complex arrangement of wheels when we have one wheel and the second one perpendicular to the first one and so on so forth. So all wheels are perpendicular to previous one, and it also allows robot to move any direction. But you can understand easily that we are not using all power of our motors to move, because at any given moment of time only two motors work and two others just do not contribute to motion. And that is why this is not really effective to have two or four motors working all the time, because it limits our speed and our power of motion. So this is not really effective scheme, but still allows you to move any direction and to have your robot omnidirectional, which is really useful because, as you saw on image here, for example, in warehouses, it can be really, really useful feature if your car or forklift can move any direction. It is especially important, as we already discussed, in confined spaces when you have not enough space to make some motion maneuvers. It is really useful and effective to have omnidirectional wheels and holonomic kinematics, which would allow you to move any direction without performing such complex maneuvers as you had to perform with a car-like kinematic, for example. Okay, so that was about omnidirectional wheel, and there's a bit more complex mecanum wheels. Mecanum is the name of a Swedish company. These wheels are called also Elon wheels or Swedish wheels. The story is simple. There was an engineer in Swedish company which was called Mecanum, and the name of engineer was Elon. That is why those wheels are called in different ways. But you can always say mecanum wheels and you will be understood by people. So these wheels are a bit more complex than omnidirectional wheels, because if here we could have a direction oriented 90 degrees or perpendicular to wheel orientation, here we can have a motion which is 45 degrees to wheel, because you can see these rollers, they're 45 degrees oriented to the main symmetry axis of wheel. And you can see that this allows us to perform also really complex maneuvers, even though our kinematics looks like typical car kinematics, still we can perform some weird and actually really useful maneuvers. And to control such a robot, we can we can use different angular speeds of our wheels. So you can see on the slide, if we have all four wheels rotating to the same direction with the same angular velocity, we will get straight motion, right? If we now will inverse two of our four wheels, so here if wheel one will rotate forward and wheel four will rotate forward, while those two wheels will rotate backward, we will have perpendicular motion, so we will move sideways. And for 45 degrees or for in place rotation, there is also really simple control rules we could apply to get all these four motion patterns. And combining them, we can have motion of any type, moving to any direction basically. So we can move straight, perpendicular, 45 degrees. We can rotate in place to change our orientation. So these wheels also allow us to operate in really confined spaces. They're really easily controllable because this is the whole kinematics equation we need to apply to control our robots. So on the right side, there are angular velocities of 4 wheels. On the left side, we will get our x, z, speed, and our angular velocity of the whole robot. So really simple equation, which allows us to control the robot and to perform really complex maneuvers. So this is a really, really short overview of different types of kinematics used in robots. You don't have to memorize all these equations. You just have to distinguish between different types of kinematics used in wheeled robotics. So there is differential drive, tricycle, also Ackermann kinematics, Ackermann steering principle, which used in cars, and car kinematics is usually substituted with tricycle, or even simpler bicycle model when we also substitute two wheels of rear axle with a one wheel in the middle. You also need to know that there are omnidirectional and mecanum-wheels. And basically that's it. That's a short overview on different types of kinematics of wheeled robots. And now we will talk about the most important concept here about probabilistic motion models. So once again, why do we need probabilities in our motion models? Why do we not just use such a simple kinematics formula to predict where our robot will end up over time and to make prediction here in our recursive Bayesian pose estimation? So I'm reminding you that this part is just a prediction, having previous system state, so previous pose of the robot estimated somehow, or maybe given to us precisely. First part of the equation, we just apply our motion model to make a prediction. So we predict where robot will be in space, given that we know some control signals. We know how much we asked robot to travel, how much we asked robot to rotate, and so on. So this is just prediction. Why do we even need probabilities here, right? So we need them because our actuators, like sensors, we discussed it previously, are not absolutely accurate. So our motors, even though they can be really, really precise, and more precise motors are, the more expensive they are, obviously. So they're still not 100% precise. They still have some errors, even though we're controlling them some signals, they do not perform them 100% accurate. And also there are different external factors which also affect our motion and also affect precision of our motion. So for example, we can have just simple geometrical imperfection in our wheels. So it is just really complex to have perfectly equal wheels. And if one wheel is bigger than another, we will have error source in our motion, and making predictions with such simple equations, we will not account for such types of errors. Now, another thing is that our operating space is not perfect. It can have obstacles of different types, and of course they will also influence our predictions of our pose. And also there can be just different surfaces such as ice, water, and our wheels can slip on these surfaces, and it also will affect our prediction. And our goal to predict our robot pose as precisely as possible, and that is why we are trying to use these probabilities directly in our motion models to account for all these types of problems and to predict not the precise position of a robot, but the probability density function. And I'm reminding you that by taking arg maximum from this probability density function, we can get our best guess, basically. So where our probability density function has a maximum, this is our best guess on our current pose, but this is still just a probabilistic prediction. We are not 100% sure where our robot is, and we cannot be. So how do we use all these external error sources, and how do we account for them in our probabilistic motion models? Let's see. So first of all, there are two major type of probabilistic motion models used. So first is called odometry-based, and second is called speed control-based. And we will discuss in a second what the difference between them. So odometry-based models are used if our robot is equipped with wheels encoders. We discussed what encoders are in our first lecture. I will shortly remind you that encoders are the sensors which can estimate rotation of our wheel. So, for example, on modern cars, we have this type of sensor because there is ABS systems and different other safety systems which can realize that we have some wheel slippage, for example, when we are braking, and can take different actions to make our braking on, for example, on icy road safer. So typical car is equipped with encoders, and once again they're used to estimate wheel rotation, so how many degrees our wheel was turned, and having that data we can estimate speed, obviously, because knowing how much we rotated in time, we can integrate and get speed of each wheel, and having speed of each wheel, we can also estimate distance traveled by our car or our robot. So encoders are quite useful source of data, but of course encoders are not precise because, as we said, wheel can slip and so on, and our estimation will be not precise with just pure encoders, but still. So if our robot has encoders, we can use odometry-based models. So odometry, this is a term which stands for estimating robot motion from encoders. And the second type of model, or second category of models, is used if we don't have encoders and we cannot estimate our robot motion from encoders, but we know the speed we are giving the robot. For example, we are commanding the robot to travel with such linear and such angular speed. If we are knowing that, we can use it for our motion modeling. Yeah, and as slide says, speed-based motion models based on calculating the travel distance given the speed and travel time. And by speed, we mean both linear and angular speed. So actually, these speed-based models were initially used in ships navigation because when we're controlling our ship or vessel, we know the speed we are commanding the vessel to move, and we can estimate traveled distance and our coordinate in sea by integrating the speed we were commanding our vessel in different moments of time. So these are two major types of motion models, and we will discuss them separately, and then we will see that they're quite equal actually in the results, so you can choose which one to use. Odometry-based is simpler. If we have encoders, we can use it. If we don't, we can use speed-based model. So what is odometry-based motion model? Let's imagine we have our robot, which moves from coordinates x, y, theta to x dot, y dot, and theta dot coordinates. So here on the image, you can see that this is initial pose of the robot, and this is a new pose of the robot. And we can compute distance traveled and two rotations. This model has two rotations. So imagine our robot was oriented where this line points. So we first rotate, which is encoded by rot 1. We first rotate, then we travel some distance delta trans, and then we rotate again delta rotation 2. So this is a model which consists on three motion patterns: first rotation, motion like linear motion, and second rotation. Of course, this is simplification, and many robots, as we saw, for example, this differential drive robot actually is moving on circular arc, and such model is quite a simplification. But for us, it is okay because it allows us to predict motion. And actually, since we are using really short delta t's, really short time increments, this straight motion, short straight motion, can approximate any complex curve, even a circular arc. So we will use this simplification in our motion models to simplify things and equations. And having in mind that delta t's are small, we can even estimate then our error in such simplification is not quite big, so we can use it. So as we said, we have encoders in a odometry-based model. So our encoders provide us following information: delta trans, so travel distance, and two rotations. As we said, encoders estimate rotation of wheels, so it is quite straightforward how from rotation we can from rotation of separate wheels we can recover rotation of the whole robot and travel distance, right? So we saw this again in differential drive. So actually, if we know that speed of rotation is similar for two wheels, we know that motion is linear, and we just integrating these rotations to calculate how much we traveled, and so on. And the same for angular rotation. Okay, so these are equations, how we estimate robot motion. And actually now it's the time to add some noise to our model. As we said, there are different external and internal factors which make our motion not precise. And we just will represent it in our model with three additional terms, which stands for noise. And here all the magic, here all the science actually, what are noise types we will use here. So there are different studies which try to investigate which noise, which shape and type of noise should be added in these terms. But in practice, there are two major type of noise used because they're simple, they're quite common for different types of actuators, and it is just simple for us to use these noise types, even though in reality the noise can be, or error can have, more complex shape. We still make an approximation here and use these two types of noise. So first one is just normal or Gaussian distribution, and second one is triangle distribution. I hope you all familiar with normal distribution or Gaussian distribution, and triangular is even simpler. We would just say that our noise can be distributed with the shape of triangle. Here is a mathematical equation which allows us giving a standard deviation to represent triangle basically. And here is this thing, we just use estimated, for example, travel distance, and we sample from distribution and add random noise here. So in practice, it means that knowing from encoders that our robot travel, for instance, 1 meter front, we are saying that even though encoders are saying we traveled 1 meter, we know that there is some noise, and to account for this noise, we will just add some random variable to our estimated travel distance, and we will have some distribution. So basically, if our encoders are saying that we traveled 1 meter, we will have a distribution, normal distribution, with a mean in 1 meter, and also some variance, and variance depends from our experience. So if we know that our motors are quite precise and the world we are operating in is quite flat, quite simple, without any external factors influencing our motion, then the variance can be small, because we are quite sure that if we are commanding the robot to move 1 meter, it will move 1 meter or something really close to 1 meter. And vice versa. If our motors are really cheap and noisy and our world isn't perfect, we have some, I don't know, complex environment, then our variance should be bigger to account for these noises, to make our prediction where our robot ended up. And then variance will be huge, and still mean will be 1 meter, because encoders are saying that we traveled 1 meter, but variance will be quite big. And as a result, we will get not a single answer on robot pose. We will predict the whole probability density function of our robot pose. And the same with angles, basically with rotations. We have two rotations. Both of them are imprecise because both of them are also subjected by noise. First rotation can be performed with error. Second rotation also can be performed with error. That is why there are also terms which are representing this error. And as a result, we will get those noisy motions, and we will have the whole complex shape distribution of possible robot poses. And we will see further how to estimate that, but I will show you here. So usually it is called banana shape distribution. And actually taking into account that first rotation is imprecise, travel distance is imprecise, and the second rotation is imprecise, with different motion noise parameters, we can get something like this. These are three types of noise of pose distribution of our robot after a single motion. So even though we were quite precisely sure where we are in the first place, after performing some motion, we will get a distribution, probabilistic distribution of possible robot poses. And here, the darker the color is, the more probable the pose is. So you can see that poses close to our predicted or expected position are quite probable, and further away they're becoming less and less probable, but still there is some probability that moving from here to here, we actually ended up somewhere here. There is some small probability because of imperfect world, imperfect actuators. So maybe any questions so far, because we're moving quite fast. Does anybody have questions? Okay. Actually, I didn't warn you that this lecture is almost the shortest one in the whole course, so we will end earlier today, and we will have time to discuss maybe previous lectures, because previous one was quite complex on Kalman filter and particle filter. So if you have some questions, we can stay after the lecture and you can ask them. So there are two types of operations we want to perform with our probability functions, with our noise functions. First of all, we want to have an instrument to compute probability of a particular pose. So here, for example, x is a particular coordinate, and sigma is a particular variance, so particular parameter of our probability distribution. And having these two parameters, we want to estimate how probable that we ended up in this pose. So for example, we are taking some position here and just asking our equation how probable that we are here. And to perform that, we use just simple normal distribution equation. We are plugging our possible pose and our variance, and as an answer we get probability, right? And the same for triangular one. I don't know if you're familiar with these equations, but this is just a simple equation which allows us to work with a triangular distribution. So we also plug our pose for which we want to estimate probability, and also parameter of the distribution, which we call here variance also. So we are plugging them into equation, take maximum, and get probability that we are in this pose. And another thing, we want to sample from such distributions. What does it mean, sample? For instance, here in our equation, imagine we have several hypotheses of our motion, right? If you remember particle filter we discussed last lecture, there we used different hypotheses. So basically we had many hypotheses on our pose, and we were moving them separately, generating different noise for different particle. And this is exactly this step. So for each particle, we are performing this prediction many times. For example, we have 100 particles. We will perform this prediction of our motion 100 times. And for each particle, we will want to generate a random variable here. So for each particle, this noise will be different, but according to the noise law. So if we know our noise is normal, we want to sample from this normal distribution different results, basically different samples. And these equations allow us to do that. So we plug number here and we get sample from a normal distribution. So we plug variance and get some result from this distribution, some sample from this distribution. And the same for triangular. So these are two basic operations we want to perform with our noise distributions. We either want to estimate probability having a particular pose, or we want to sample from a distribution to generate particular pose with these equations, having our estimation plus some noise. And these two operations allow us to have quite different representations of our motion models. So this is an example of sampling. If we will sample from this triangular distribution many times, so having the number of samples represented on the slide, we will, and plotting each sample, we will be closer and closer to real triangular distribution when the number of samples grows. And the same with normal distribution. If we would use this equation many times and just plot different samples, different numbers we get from this equation, we would get something really close to normal distribution. This is sampling. So we're just asking a distribution to generate some number which is within this distribution. And having these two operations, we can have two different algorithms, which actually one is inverse of another. For example, first one, imagine we have our odometry readings. So something our odometry or our encoders are saying about our motion. So estimated motion, which is estimated by using some sensor readings. And we have our hypothesis. For example, somehow we predicted that we have to move to this position. And now we're actually having both of these two. We want to estimate how probable that our hypothesis is correct, or how probable our hypothesis is given the odometry. So for that, we are using these equations we saw previously for our motion model, which has two rotations and one linear motion. And we estimate parameters of our motion using first our hypothesis and then our odometry. So you can see that the equations are the same, but we are just plugging either prediction made with odometry or our hypothesis made somehow. This is just a hypothesis, right? We just take a random place, random coordinates in space, and saying that this is our hypothesis. We think that our robot is here after some motion, and we use it here. And then using these equations, basically, or equations close to this if we have more complex probability function, we're just estimating how probable each parameter, how probable that rotation is the following, linear motion is the following, and second rotation is the following. And here you can see differences between hypothesis and odometry. So plugging differences here, we get a probability that probability of such a motion. So basically, if the difference between odometry and hypothesis is huge, then we will get somewhere here, for example, and our motion probability will answer that this is not quite probable, right? But if the difference is small, we will get somewhere here, and it will have big probabilities. So basically, what we are doing here, we are trying to compare estimated and predicted motions. And if they're quite close, then the probability will be huge. If they're quite different, probability will be small. And since we have 3 parameters here, the total probability is just a product of those 3, because we consider them independent. So we independently rotate, independently move straight, and independently rotate once again. We consider all these 3 motions independent, and total probability is a product of all these 3 probabilities. So, and this is first, actually, this is the first type of our probabilistic motion model. This, the whole function here is a probabilistic motion model. It allows us for our given hypothesis, which can be any predicted place, and given odometry readings, to predict probability of some motion. So once again, we can sample any point in space and ask this function how probable that our robot is here according to odometry readings, and we will get an answer. And this function is actually something representing this motion model. You see, we have our previous state, we have control signals, and we can, for any given place in the world, we can answer the question how probable that given previous state and motion parameters, we ended up in this place. So this is the first type of motion model, probabilistic one. And vice versa with sampling, since we had probability here and sampling, 2 different operations, we can use another type of motion model. Here we're doing the inverse thing. We have our control signals, so we know how much we asked robot to rotate once again, and to move straight. We can sample some noise from our models with these equations. So basically, we are sampling from this or this probability function. And then using these noisy parameters, so we basically add some noise to our parameters. We know that we commanded robot to rotate, for example, 90 degrees, but we add some noise because we know that our motion or rotation is noisy. So we add some noise, and then we use these noisy parameters to calculate kinematics of the robot. And this is our answer. We get some point, a single point in space, which is our prediction, which already contains some noise. So basically, we generate random noise and predict a single noisy pose in space. And we can repeat this operation many times to get some discrete samples. And this is a difference. So with the first model, we get something continuous, because for each point in space, we estimate probability using this product of 3 probabilities. We perform this operation for different hypotheses, and by hypothesis, we can mean all like places in space. Of course, we discretize some our space with some discretization factor, but still, we can ask this question for every coordinate, every combination of coordinate, and we can have something quasi continuous, right? This is the first model. And with the second model, we just use discrete samples, so we can perform this operation also many times, every time predicting some point in space, and we'll get something like that. And you can see that these models are quite similar, but here we have something continuous. Here we can have something discrete, but we can use both of them. So both types of odometry-based motion models are used, and they're actually really the same. They're just inverse. In one model, we use probabilities, we estimate probabilities. And in another model, we use sampling from probability functions to estimate pose. That is why it is discrete. So these are 2 types of odometry-based motion models. You will have to implement one of them in your second homework, but it will be even simpler than here, you will see, and it also almost will be implemented for you. You will just need to plug some motion parameters, and you will get a probabilistic motion models quite similar to this ones, also with a banana shape distribution and similar shape and equations. So, are there any questions so far? Okay, let's move further then. So far we discussed these two models, which are both odometry-based models, because here we had our motion parameters given by odometry, and here we also had odometry as an input to our model. So there is some sensors which allow us to predict or to estimate where we are. So this is our expectation, because we have some sensor or sensors which are saying that we moved so far. In a second type of models, which are called speed-based motion models, we don't have encoders anymore. So such a model assumes that we control the parameters of the robot motion, linear and angular velocity. We don't have sensors to estimate anything about our motion, but we know how fast our robot is moving because we are controlling linear and angular velocities. In this model, robot moves along a circular arc. Here we had a simplification that our robot moves on a straight pieces, but they're quite short, so we can represent circular arc with this short straight motions. Here we directly have circular arcs because of our equations, because here we have linear and angular velocity and we have to move on a circular arc. In this model, our speeds will be subjected to noise. Here we had our motion parameters, rotation and transition, subjected to noise, and here samples of noise we were adding to our motion parameters. And in these speed-based models, directly speeds are subject to noise. So on the right side of the slide, you can see linear speed with some noise and angular speed with some noise also. But actually we will have to add third artificial parameter to our motion model because we want our robot to be able to rotate in place. And as you remember, for example, if we are using differential drive, our robot is able to rotate in place. And with this circular arc motion, we cannot represent such a maneuver. That is why we are introducing third parameter, which is just an additional rotation angle, and we consider this rotation being performed after the initial motion with constant velocity and constant angular velocity. We add some additional rotation, and it also subjected to noise. So to estimate motion of our robot, these are equations we have seen in the first part of the lecture in kinematics. This is just a simple equations which allow us to estimate x, y, and theta given delta t and initial motion parameters. And you can see here that we have, instead of radius, which we had here in the first part of the lecture, we now substitute radius with fraction of linear and angular velocities, which are obviously equal, and that's how radius is computed. But since we are controlling these two parameters, we want them to show up in our equation. That's why we are substituting radius here by division of these two. And then again, we can have two different inverse motion models for the speed-based motion model. In the first one, we're estimating probabilities of our motions. And again, by multiplying three probabilities, we're getting the final probability for any given place, for any given xt, which is pose of the robot, x, y, and theta. we can estimate the probability of robot being in this place. We will not stop on these equations. This is just a simple geometry which is derived from this equation. And vice versa, we can sample from noise again. And as we discussed, we now have three parameters: our linear velocity, angular one, and final rotation. And we can sample from our probability error noises from normal distribution or triangular distribution once again, add this to our speed we're commanding to our robot, and using this equation just compute kinematics and return pose we get by adding this noise. So for example, if we commanded our robot 0 angular speed and 1 meter per second linear speed, by sampling from some noise model, we will add some additional factor here. And also, even though we are commanded 0 angular velocity, we will get some angular velocity by sampling from our noise model. It can be big or it can be small. And then we also will get some final rotation, small one. And as you can imagine, we will move not to the place we were planning to because of these samples of noise. And by recovering the final pose, we will get something really different from what we expected. And this will be a single sample. And by repeating the whole operation many times, we can get many samples like that. And these samples, this discrete set of samples will represent our probability density function. Or with the first equation, we can get the probability density function right away, continuous one. The choice of which motion model to use depends on your particular task, on your computational resources and so on. And it is obvious that discrete representation is less computationally hard, but it is less precise compared to the continuous one, also obvious. And we can compare odometry-based model and speed-based model, and we will see the distributions we are getting for the same type of robot are quite similar. And you can see also that here we were considering robot moving with 2 rotations and 1 linear motion. Here our robot moves using arcs because of these motion equations and because we are controlling linear and angular speed, and the combination of linear and angular speed gives us circular motion. But still, the distributions are quite similar, which for us means that we can use both models. They're practically the same. The choice of one or another only depends on either you have encoders, and then it is simpler for you to take real readings from real encoders, because they already say tell you something on your motion. Or if you don't have encoders and you have your robot without any sensors, basically estimating motion, you can get just speed, linear and angular, commanded to your robot to estimate your motion. Of course, it is always good to use sensors if you can, because they're more precise than just commands, because sensor readings already have some estimation. They already performed some estimation on your pose. And if you just use commands, this is just something virtual, something you're commanding your robot. But still, you can see that models are quite the same and we can use both. And one of these models you will have to implement in your homework. And I hope that by implementing it in code, it will get like more obvious for you how all these things work, because the description here is quite complex. But for now, it is important to get the concept that by adding some noise to our expected motion, we can get some distributions of probable poses where our motion ended up. And this is the first part of this Bayesian estimation. So this first part, having our previous pose and having our control commands, which can be real control commands like linear and angular velocity we are commanding to robot, or which can be substituted by sensor readings. So basically we substitute control commands by something we already estimated with sensors, we can estimate the first part of the equation, and this part actually gives us our prediction. So this first part before integral, this is our prediction on where we moved with our robot in the previous time interval. And then in the next lecture, we will discuss how to correct it with the sensor readings and using observation or measurement model. So here we actually lose some information, as you can see. We started with something really precise. So initially we knew the pose of our robot quite precisely, right? It can be also a distribution, but still we consider that we know some pose of the robot which we take for granted as a current pose. And we lost some information because started from something really precise, we ended up with some distribution. So we are less sure on where we are in space after some motion. And it's quite straightforward. If we are moving in space with some noisy motors, of course, we are becoming less sure on where we are in space. I think it is intuitive for you. And the second part of the equation of Bayesian estimation will be about how to make our estimation more precise on the next step. Because we have not only motion, we also have sensors placed on robot, some lidars or cameras. And using these sensors, we can somehow to become more sure on where we are. And this distribution should have less variance. It will be more condensed after second correction part of Bayesian estimation, and this what we will use for next step. So since it is a recursive estimation, every step we are losing some information with motion. So we move, we become less certain on where we are, and then we correct it with external sensors readings, and then we move again and again, lose some information, gain some information, and so on. And this is like infinite cycle when we work with robots which move over space. They always become less certain, and then with sensor readings, they become more certain on where they are. And the last small notion here in this lecture is that there are more complex motion models than we discussed. Obviously, there can be more complex probability noise probability functions. Not all noises, not all errors are normal or triangular. You can have any complex shape here. If you know that, for example, the error model of your motion is multimodal, and there is not a single Gaussian distribution but a mixture of Gaussians, you can still represent it. But this equation will become more complex, and then this probability estimation and sampling will become more complex. You will have to program it somehow. And obviously these models which use either probability estimation or sampling, they also will become more complex. But it is possible, and there are models which are more complex than these two simple noise models we discussed. These are just example, and the first choice usually is a normal distribution. If you don't know some distribution, you usually just use normal, and it often works fine for you. Of course, the more precise your distribution, basically more precise your motion model, and less uncertain you become when you move. And this is obviously good. If you know something on your motors, on your environment, you can directly encode it here in your distribution, and then you will become more certain when you're moving. And to estimate this distribution in practice, actually, people just perform experiments, because by assembling robot, which is like many motors, complex environment around, you cannot analytically estimate this distribution. It is a really complex problem. That is why usually people have their robot built and then experiment. They try to move robot 1 meter, for example, 1,000 times, and they get some distribution like this one, right? And having this distribution analyzed experimentally, they're trying to recover this noise model, because you don't have any other technique to estimate your noise model, only experimentally. There are analytical noise models which you can use, but they work only for really restricted types of kinematics and so on. You can find them in books, but in practice, people usually do vice versa. They perform experiment with real motion and they try to recover this noise model, and then they use it in these equations to predict further motions. And the last thing here is that there are also some modification to motion models. For example, this is the one taking environment into account. For example, imagine we have our motion model, which gives us this banana shape distribution. And imagine we have a map, right? Because we actually in motion model here, we don't use a map. We remember that we have it. We will use it in observation or motion model to compare what we measure with our sensors with the map and to make a decision on how similar these things are and how probable that we are in this place or in another place. But here in motion model, we don't use map usually. But why? Because map contains some important information we actually can use even in motion models. For example, if we get a distribution on some particular step, right, we are predicting our pose and we get some distribution, we can consider obstacles from a map, and this rectangle represents an obstacle. And if we know that there is an obstacle, we obviously can exclude this part of distribution because we know that we cannot end up inside an obstacle, right? Our robot cannot be inside the wall, for example. And that is why we can modify our distribution after generating it to exclude the part which intersects with an obstacle. And this gives us a lot because on the further steps, when we will use our correction step with a motion model, we will not we will not have to work with part of distribution which is improbable, because having just that, we will have for each hypothesis or for each pose of the robot, probable pose of the robot, to correct the pose with measurements of sensors. But excluding part of distribution just simplifies our tasks, because part of distribution is improbable and we can estimate it beforehand, which is quite good. And this is this thing, talking mathematically, this probability, which is probability of a current pose given previous pose and control signals, is not equal to this probability where we also consider map. And this simple examples show you how to consider map. We can just use it to exclude part of the probability right away to simplify our further work with this probability. So that's basically it for this lecture. As usual, you have some additional resources to read. The first one on differential drive kinematics. The second one is a chapter 5 from Probabilistic Robotics, which you can find in Piazza. Chapter 5 is dedicated to motion models, so many pictures on these slides. These ones, for example, are from this chapter, so I suggest you to read it because it has more rigorous explanation of what is going on here and what is probabilistic motion models and why we need them. And also there is a nice presentation on different kinematics and different types of robots, and there are also some really interesting concepts which you can check out if you just want to know more about different types of robots. For example, there is a concept of VEX, which is combination of wheel and leg. And there are robots like that. I think you could see some Boston Dynamics videos, for example, where they have robots with legs and which have wheels on their ends. So just a really nice presentation you can use to find more on different types of robots. So that's it for today. If you have some questions, let's discuss. Where do hypotheses come from? I see the question in chat. So you mean, for example, this hypothesis, right? Okay, let's consider that we're talking about this hypothesis. So these are just our hypotheses generated somehow for our pose. We can just, I don't know, use random numbers to generate hypotheses. Or there can be different strategies. For example, we can consider as a hypothesis every possible pose around our predicted position. So first of all, we know our encoder's readings, right? So we know estimated pose. But then we're trying to generate distribution around that because we know that we are not precisely in this space. And we can just check for any position around this place and call any position, any combination of X, Y, and theta a hypothesis. Or there is another approach. Last time we discussed particle filter, right? And this is the actually most popular algorithm working with particles or hypothesis. So see what we are doing here. Imagine we are starting with, let's say we have how many? 7 particles here. So at the first or initial moment of time, we somehow initialize our particles. For example, if we have a map, imagine this rectangle, actually our map, right? So we can generate 7 hypotheses on where our robot is in this map. And how we generate them in the first initial time moment depends on what we know. For example, if we don't know anything about our robot pose, we just have a uniform distribution. We just put one particle here, another here, just randomly. So imagine we initialized our filter with our particles, right? So just randomly putting them on the map. The second step here, for each particle from n equal 1 to n, where n big is n capital is a number of particles, we're sampling from our motion model. So we take a position of each particle as an initial position. We take our either encoder readings or our commanded linear and angular velocity, and we move our particle, adding some noise. So here in this equation, hypothesis can be particle. So for each particle, we know some particular position where this particle is. Then we move it, and we know new position of a particle. And this is our hypothesis. And here in this simple toy example, we would have some 7 particles. For each, we know current position, and we know where this particle traveled, because we know commands we are giving robot, and taking position of a particle as a starting position and applying commands or applying encoder readings, we know a new position of a particle. And each particle is a hypothesis, and that's how we generate them. And moving further through particle filter, let's remind ourselves how it works. The second step will be observation model, which we will discuss on the next lecture. So in observation model, we are taking sensor readings, compare them to the map, given the prediction of a pose. So again, for each particle, we will take pose of this particle as a real robot pose. We don't know either it is correct or not, but we will think that position of each particle is a correct position, and we will use it to see on the map what robot expect to see or expect to measure in this particular particle position. And comparing it with sensor readings, we will make some decision, either they look close or not, and this will generate probability of weight of each particle. So this is really simple, actually. For each particle, we're taking its position as real position, comparing on the map what we should see and what we are seeing with our sensors, and making decision how probable this pose is. And you can see some poses or some hypotheses become improbable, and some become really probable because the sensor readings are really corresponding to the map. And that's why we are making decision that particle is quite probable. And then we just kill particles which have low weight or low probability, and multiply particles which high probability, so the total number of particles always stays the same. And we do that with a procedure called resampling we discussed last time. It is probabilistic also, so even particle with small weight can survive sometimes, but it has lower chances to do that because of its small weight, because it's like roulette. I hope you remember the analogy from last lecture. So did it answer your question on how we generate this hypothesis? So if we are talking on particle filter, and we better to do that because this is a particular algorithm which is really common. Hypotheses are our like discrete hypothesis or discrete particles. Each particle is our hypothesis on robot pose or robot state, because it can be applied not only for wheeled robots, but also, for example, for arms. And arm also has its state, which is represented by angles of joints. And we also can do the same. We can have a prediction or particle or hypothesis on how our states, how our robot is, which state our robot has. And then we can correct this hypothesis by some measurements. So you will have homework on particle filter. So I hope it will be more clear for you after this simple homework. Okay. Any more questions? Maybe on previous lectures on localization, or when will be the homework? I think I will distribute the first one during this week. So basically, there is no deadline for homework. I mean, you can try to pass it till the end of the term. You will have 3 homework as we discussed. First one will be on Kalman filter, and it will be really simple. You will just need to fill matrices which represent again, which represent system state and control signals and measurement model H here. So you will have all Kalman filter programmed, and you will have just to fill the matrices depending on the description. So there will be description of some system, for example, a car traveling straight forward with a constant speed, blah, blah, blah. You will have to fill these matrices and then just make some conclusions on how Kalman filter worked for your system. This homework I will distribute during this week, I guess. Yeah, I will distribute it till the next of this week, but there is not final deadline. The deadline is the end of the term. By the end of the term, you will just get some scores for all homeworks, and you have infinite tries to pass the homework, to answer my questions, and so on. And second homework, I think, will be in the end of February, and the third one, I guess by the middle of March, something like this. So you will get a notification from Piazza. I will put homeworks there, and I will try to remember to also let you know through Telegram that I put it, but you better check the Piazza for homeworks. Okay, many more questions? Okay, so remember that you can always reach me in Telegram or Piazza with questions. If you have some, don't hesitate to ask. I'm always online. Have a good week. So see you in a week on the next lecture. Bye. Oh, there is. See you. Bye-bye.